the early words, which is welcome again to the Cryptolog series, and this session is being recorded, and it will be on YouTube. I believe you signed up on. So don't ask any wildly internal questions, and if you have such, just ask after. I think we're going to lunch after this. Everyone's of course welcome to join. I guess usually I always want to say that if you're not a member of the Cryptalk Alliance and you want to get announcements for these talks, just add yourself on IT Web. Yes, so just do some intro. Yeah, I don't even know what to say about Melissa. She's so accomplished.
I don't know.
Like which one of the numerous things. All right, so today we have the pleasure of having Melissa Chase here give us a talk. Melissa is a longtime colleague of ours here at Microsoft Research. She works on all kinds of cryptographic protocols, protocol security, has contributed to anonymous credentials, has contributed to end-to-end encryption, key transparency. In addition to the amazing work that she does here at Microsoft Research and at Microsoft, she has also helped basically contribute ideas to Signal and WhatsApp. Now, today, she's going to talk us about something really interesting. It's a project from a few years ago about ad privacy. I hope this is interesting to everyone. So take it from here.
All right. So today I'm going to talk about a project called Precio. And this is joint work with Eric Anderson.
Can you turn your mic on?
Oh, yes. Thank you. Trying again. Okay, so today I'm going to talk about a project called Precio. This is joint work with Eric Anderson, who's here at Microsoft in Edge, Batul Darak, here in the room, and Amasara, Kim Laina, and Jen Kai Wang, who is our intern and is now faculty at Arizona State University. Yeah, so this, I'm going to, as Kim mentioned, this is a problem we looked at in the context of web advertising, but we think that this protocol is also more generally interesting. So before I start into it, I'll just mention that one of the related works, Precio, has been used for other problems like telemetry collection and some of the contact tracing things during COVID. So yeah, should hopefully be more generally applicable, but for today I'm going to talk about it in the context of web advertising because that's the context that we were looking at the time. Okay, so the web advertising picture. So the way the web works today, you visit different websites, they can drop cookies, but they also probably contact some third parties for scripts and ads. Those third parties can also drop cookies. And then if you return to another website that contacts the same third party, they can read the cookies again. And that allows essentially these various ad platforms and other third parties to collect a lot of detailed information about what you're doing on the web. Yeah, because every time they can read the existing cookies and put new ones. So this is good for some things, but it is not good for privacy. So in particular, that means that there's some entities who you're probably completely unaware of who are building up these detailed records of everything you're doing online. And in particular, some parties may be using this for legitimate purposes, but there's also a lot of potential for abuse. On the other hand, there are good things we can do with it. So one thing is, we want advertising to work, and as part of that, the advertisers want some kind of information about how their ad campaigns are doing. And so one of the things that cookies are used for right now is, the ad network can basically build a detailed profile of you of different demographic information. And then when you click on an ad or when you make a purchase as a result of clicking on an ad, call that an ad conversion, then they can basically track everybody who has, as a result of an ad, made a purchase or something like that, and then they can show the advertisers detailed information on who's clicking on their ads, and how much money they're spending and things like that. And so from the ad perspective, this advertiser's perspective, this is really useful. It lets them sort of improve their ads, ad campaigns, and sort of decide where to spend money. So from their perspective, they're going to get a dashboard sort of like this. This, I think, is one of Google's version of dashboard, but a number of different companies make these. So you can see, like, they can partition the data in a bunch of different ways. You can have different kind of graphs. Here we're partitioning by device type, by the country that the user is in, operating system, browser. And then these are usually, they're you can make adaptive queries. So the analyst can look at this and be like, okay, I'd like to focus in just on desktop users, and then we get all these, things. Statistics based just on desktop users. Or they could say instead, I want to focus just on users in the US. And then you get, again, everything sort of recalibrated just for the users in the US. And then you could sort of recursively filter and say, okay, I want desktop users, and then I want to maybe just look into the desktop Linux users or something like that. And again, you get all these statistics just for the specialized set of users. So it allows for these nice flexible queries. And so what we're trying to look at here is how can we get this kind of functionality but with better privacy for users, and in particular without third-party cookies. And I'll just say, if anybody has any questions at any point, please stop me. It's more fun when people ask questions. Okay. So what's the idea for how we're going to do things without third-party cookies? So the first idea, and this is, I think, a bit coming out of Chrome, but also Mozilla. But the basic one of the ideas is that we're going to have, instead of every time you go to a website and the tracker sees your cookie and can build this detailed information on the back end, we're going to instead say the browser is going to build that information locally. So we'll still be able to build up this sort of demographic information, but it's going to be collected on the user's browser instead of collected by some unknown tracker in the back end. So that's sort of better. It gives the user some control because it's local. But still, when we want to do when the user, say, buys a product and we want to compute these statistics, the browser would then send a report saying, okay, these are all the demographics of the person who bought this. This is what they spent. And that's not amazing because then here the reporting origin is what I'm calling it, but think of that as the ad network. Now gets all these detailed, demographics about you whenever you make a purchase as a result of an ad. So that's not great. So the proposal is actually instead a bit more complicated than that, which is that instead of just directly sending the reports to the reporting origin, we'll instead essentially encrypt them to some aggregation service. And there's actually different proposals at the moment for how to implement the aggregation service. There's sort of one line of work that's looking at trusted hardware, which I'm not going to talk about today. But there's another approach, which is using cryptography, so specifically multi-party computation. So there we're going to say, okay, we have two servers. They're going to be run by two entities that we think will not collude. So think of two different, like Microsoft and Google or something like that, or Microsoft and Mozilla, or potentially it could be a, third-party nonprofit sort of entity. And so now the browser, instead of just directly sending the report in the clear to the ad network, they're going to secret share the report. They're going to encrypt the secret shares, one to each of these servers, and then they'll send those encrypted secret shares to the report. And now the reporting origin, rather, so the ad network. And now the ad network can send these secret shares over one to each of the servers in the aggregation service, and then they're going to perform some kind of cryptographic protocol to try to compute and aggregate it. So the nice thing is here, nobody actually gets to see the user's demographics in the clear. So that's sort of the general picture we're trying to achieve. We're going to consider data sources as completely malicious because really we have no great way of ensuring that you're actually joining from a legitimate browser. So somebody could be spoofing a browser, and we don't want that to mess up the results or affect privacy in any way. We're going to think of the reporting origin, so the ad network, as malicious mostly. So malicious for the point of view of privacy. So we want to say no matter what they do, so they can't compromise privacy, but we're going to say if they mess things up, if they decide to, they may get incorrect aggregates. They should still be private, but they may be incorrect. Which I think makes sense because this is the entity that actually wants to learn the answer. So if they want to mess it up, then that's their problem. And we want to consider them being malicious because we want I think one of the goals of this kind of system is you still want to support all of the ad networks that currently exist. You want to exclude any parties when you're moving to this more private version. Otherwise, there's various issues. So that means that you can have some of these smaller, less well-known, less reputable entities. So we still want to allow them to be able to compute these aggregates, do ad conversion measurement. So we want to be able to allow for malicious entities there. And then, right. And then what we're going to say is that the aggregates they get back from the server should be differentially private. So that's the sense in which we're going to say they should hide the user's privacy. So they have to reveal something about the users because we are trying to compute actual information in aggregate about the users, but it shouldn't reveal anything about individuals. And right, we already said that. Okay. Yes. Yes, please.
When you say that the browsers, the data sources can be malicious, is that like full malicious, like I'm trying to poison the data from
Yes.
the browser? Okay, great.
Yeah. So they send something up, and the adversary could generate that in any way they want, and particularly we want to make sure that they can't like send one bad entry and completely botch up the results.
Yeah.
So I mean, always they can make up fake demographics, and we can't tell fake demographics
Sure.
from real demographics, but we want to say they can't swamp the results.
Okay, thanks.
It's kind of interesting to compare how this, what the differences are to the tracking cookie-based solution here. So I guess if you use the third-party tracking cookies, you can always delete your cookies and you can mess up that process. But I suppose in that model, any kind of data reporting is done by some web servers, maybe. When you do some action, they report. Here it's nice that, of course, you have the control to, put whatever you want in your report if you choose. So I guess the browser wouldn't expose that probably normally to users.
Yeah, I don't know what the plan is for sort of the UI for the browser side of this, but you could potentially exclude certain browsing from the demographic collection or change your whatever data is there, or at least view it. I don't know what the plans are at the moment, though. Okay, any other? I'll move on. Okay, so just maybe one more thing to mention is for the purposes of our protocol, we're considering these two servers in the aggregation service to be semi-honest. So that means they follow the protocol, but they may try to learn extra information. And we're actually going to change it and add a third server because that makes things more efficient. So we're going to assume we have 3 servers, and they're all semi-honest, and they're all independent. So you could think of this as, say, 3 large reputable organizations. And we're also going to say that they can, I don't know if I said that already. No. So potentially one of them could collude with the reporting origin, because it's quite likely that some of the entities running these servers would be like the major, like maybe Google or Microsoft or some of these other, Mozilla, some other like major ad providers. But we're going to assume that they don't collude between one another, and that they're following the protocol at least. And potentially you could ensure that with some extra auditing or something like that. Okay, so that sort of takes care of the system setup. Then I'm going to get a little bit more into what exactly we're computing and how it compares to previous work. So I guess the first thing is that when I said that you're sending these reports, which are sort of demographic profiles of the users, in more detail, we're going to think of those as just like a long bit string that can be broken up into some number of bits corresponding to different categorical attributes. So those are like things like the things we're filtering on. So like device type, or browser, or country. So here, like the first 4 bits encode the device type, the next 6 bits is country, and so on. And then we also have numerical attributes, and that could be things like the amount you spent on it, or something like that, the amount of money that you spent, or the number of items you purchased, or something like that. So the idea is we want to filter based on the categorical attributes, and then aggregate based on the numerical attributes. So now I guess I want to compare briefly to prior work. So the one that's been around the longest and actually been used in some places is something called Precio, which is very cool. But the interesting thing is the way that they encode their records are all numerical attributes, so things that you can aggregate, and basically it's a vector of numerical attributes. And then you can, the aggregation is essentially adding them all up. And so that can be good depending on what you're trying to do, but if we're trying to do this kind of selective filtering thing where we want to say, oh, I'm going to filter on these 2 categories or these 3, that's going to be very expensive because you have to know when you're encoding the record. So when the browser is encoding the record, they have to know already essentially what queries are going to be made. So they have to already have a column to add up for, say, desktop users with Mac and Chrome or something like that, and so on. So if you wanted to be able to compute arbitrary combinations of things in that diagrams in that initial picture I showed with the different charts, you'd have to have a separate column for every possible combination of attributes you could have. And that is gets exponential pretty fast. So it may work well if you already know before the browsers even encode the records what you want to compute, but it's not good for this kind of flexible aggregation. The other approach that's being considered is based on incremental distributed point functions. And there you can get a little bit more of this sort of progressive filtering. So basically you can think of the records are a list of categorical attributes and then a single numerical attribute. And then the kind of functions you can aggregate is you can basically first filter based on the first field, and then you can just, so first you filter based on device type, and then you can sort of decide to go a level lower, say, and decide to filter some of those device types based on country and so on. But it's all sort of in order. You have to first, it's like a tree. You have to first filter on the first attribute, and then filter, partition on the second attribute, and so on. So you could, in this example, you could compute desktop US Chrome users or desktop US users, but if you wanted to compute some statistics over all Chrome users, you'd actually have to compute all possible combinations of device type and country with Chrome. So that becomes, again, much more expensive. Right. So, okay, so what we want is completely flexible sort of filtering and partitioning and then aggregation. So we have device and reports. In my example, there's 16 bits each. They could be something else. So say we want to first partition by the country, so which is the first 6 bits. And then we want to, maybe the analyst decides he's really interested in those Australia results, then we should be able to look at those Australia results and partition based on the browser that people are using there, or something like that. Now, again, we should get a nice graph like that where we get counts for how many entries are how many users in Australia are using each of the browsers. And I think, so something interesting about our approach, so the previous 2 approaches, both Precio and the distributed point function approach, they actually do the same, even though, you're building, even if you're trying to build this kind of like, well, I guess Precio doesn't really have a way of doing it, but the DPFs, even though you're building this sort of hierarchical partitioning thing where you first partition based on this and then you partition based on this, you're not actually partitioning the results at all. You do the same operation to every user record. And it's just that at the end, what the answer you get tells you the number of things that were in this specific category or combination of categories. In contrast, what we're going to do is actually partition the records. So instead of just doing some computation based on the result we want to, the partitioning we want to do, we're actually going to take each record and figure out which bucket to put it into. So we call it bucketization because of that. So the advantage, I think, is that if we first put records in different buckets and we have a bucket for Australia, now we say we don't at the moment even need to look at the other ones. What we want to know is what's happening in Australia. Now this sort of second phase of the protocol only has to deal with a smaller number of records that have to do with users in Australia. So it's sort of nice and easy to recurse because things get smaller as you go down. The challenge, of course, well, one thing is, this is a challenge for everybody, but we want to hide the exact counts that are in each bucket, and that's harder when you're actually putting things in a bucket. You can see how many things are in there. And then we want to hide, of course, which record goes where, because if you can see that, we'll put this first user record in here, and particularly if the aggregation servers are colluding with the reporting origin who got the record from a particular user IP, then that reveals exactly which user has this combination of attributes. So we don't want to do that. Okay. So I'm going to just very briefly tell you intuition for how we solve those problems, and then I'll go into detail about how the protocol works. So I guess the first question is how to hide the counts, and this you may have already figured out. Basically, we're going to use differential privacy. We're going to add a bunch of dummy reports in each bucket. So essentially, instead of getting just the count of real reports for Australia, we're actually going to get the count of real and dummy reports for Australia. You'll see that real and dummy reports in the bucket, and you can count them, and that'll give you sort of a noisy count, which aligns nicely with differential privacy. And then the second problem was this idea of that we want to hide which record ends up in which bucket. And here, now that we've added these dummy reports, we also want to hide where the dummies end up. Because if you know this record is a dummy, then you can just count up all the dummies, and you have the exact count again. So for that, we're going to use what's called the secret shared shuffle. So basically, it takes a bunch of secret shared inputs, and then it produces resharings of the same inputs in a different random order. So that's like high-level intuition. So now you put in a bunch of reports and dummies, you shuffle them all up, and then you partition them. And then as a result, we don't know what went in which bucket and what is a dummy. Okay, so that's like the sky-high version. Going a little bit more in detail, I'm going to describe this I'll call it the baseline protocol, which is something by Muslim and Gordon. And so they actually were trying to solve a somewhat more complicated problem, but as part of their paper, which I think was something like differentially private access patterns. But as part of their paper, they proposed this protocol, like in a little subsection of, you could do this. They're not aiming for efficiency, they're sort of aiming for a theoretical result. So they just say you instantiate all the building blocks with generic two-party computation. So that's something that we're going to have to work on, but at least the basic idea is really useful. Okay, so suppose we have a bunch of secret shared data. So this first column is supposed to be what the first server has. The second column is what the second server has. And each row is a record, and so you have two shares of the same record. And we know we want to partition on a particular set of bits, so say the third through the fifth bit or something like that. Those encode the attribute we want to partition on. The first step is that the two servers are each going to add dummy reports, or actually, I guess they're together going to, in this protocol, they're together going to add dummy reports for every possible value of the attribute bit. So you say, the attribute is in bits, bit positions 3, 4, and 5, and so I'm going to think, okay, that's 3 bits. So consider all possible values those 3 bits could take. So you have 8 possible values, and for every one of them, I'm going to sample some random number, and that's going to be the number of dummy records I'm going to put that have that attribute that I'm going to add to the data set. So now we have our original data set, and we have a bunch of dummy reports added at the bottom. Then the two parties obliviously shuffle the data set. So basically, they shuffle it, and they re-randomize each of the secret sharings. So what you get is new secret sharings of the original entries in a random order. So now it looks more like this. And the servers now can't tell which of the entries correspond to dummy records because they're re-randomized sharings. And then we'll reveal shares of the bits we care about. So that's bits 3, 4, and 5. So actually, I guess there's only 2, so say 3 and 4. And then so we're going to do all our secret sharing bitwise. So this works really nicely. We just reveal those bits. And then they can reveal those to one another. Then they can combine the shares, and that reveals the attribute. And they still have the shares of the rest of the record. And so they can sort of partition the shares of the rest of the records based on the revealed attributes. So everything where the revealed attribute was 0, 0, put in the first bucket, and so on. And that already gives us sort of noisy counts, right? Because we can see how many entries got put in the first bucket and second bucket, and so on. And then if we want, we can also potentially aggregate. So I think you have secret shares of some numerical attribute in all the records in one of the buckets. You can add those up. For them, they say you add them up under generic two-party computation. And that gives you a total for every bucket. And then the cool thing is now we have things sort of partitioned based on buckets. So now we can think of recursing and saying, okay, I'm going to look at everything that has attribute that attribute equal to 0, 1, and I'm going to do a whole new partitioning, a whole new run of this protocol within that bucket. So that's a basic approach. Maybe can I ask if there are any questions so far on that? So then if that sort of makes sense, then I was going to talk about the sort of two challenges that we had to look at. The first was how to do these steps efficiently, because as I said, the paper just says use generic multi-party computation for everything. And then the second thing is sort of when we want to recursively partition, how do we make sure that things don't blow up? So how do we manage noise and keep things efficient? Yes?
Is the noise added uniformly or does it depend on the data?
I'll get to how the noise is added in just a slide, yeah.
You just threw it at the end. The paper says, do all this with generic multi-party computation. I haven't seen anything yet in this, I may have missed it, that requires multi-party computation.
Oh, well, like, for example, each of these steps. So you're going to add some number of dummy attributes. So they say, how do you decide how many dummy attributes? We're going to sample the number under multi-party computation. And then generate the dummy attributes under multi-party computation. And then I think they sort of pad up to some maximum. And then when you have to do the secret shared shuffle, they just say, oh, multi-party computation. And then when you have to aggregate, again, you just say like, oh, generic multi-party computation. So they don't look at how you would actually instantiate any of those things. So what we have to do is like look at exactly what we want to use for each of the steps.
It feels, I may be completely off. It feels to me like the shuffle could be done with a traditional shuffle without multi-party computation is slow and complex compared to a shuffle.
Yeah.
And the aggregation could potentially be done homomorphically.
Yeah, exactly. So each of these things could be done more efficiently, and what we're going to look at is just like what is the best way that we could find, mostly using existing techniques or at least variations on it for each of these steps to make it efficient. They just don't even look at how to do that. But yeah, it's nothing that's like completely radically new or anything like that. Yes. Okay. So I guess the first step is adding dummy records. So I guess the first question is, what do you want the number of, how do you sample these dummy records, I guess, like what do you want it to look like? So basically what we're going to do is for every possible attribute value, we'll choose the number of dummy records from a Gaussian distribution. We pick Gaussians because it sort of aggregate, the differential privacy guarantees aggregate well when you make many queries. So for every possible value of those 2 bits or whatever it is, so all 4 values, you're going to choose a number of dummy records according to a Gaussian distribution. And then, I guess here we got 3 bits. And then what we're actually, I guess the first observation, they do this sort of jointly under MPC. The first observation that we make is that those 2 servers can actually independently sample dummy entries. Now we end up with twice as many dummy entries, but we don't have to do so much under the multi-party computation. So in particular, say this is server 1, they choose this number of dummy entries, they'll put all these reports down here at the bottom, and they'll tell server 2 just the number of dummy reports total over all bins that they're adding. So now the server 2 will just add a bunch of zeros for those entries. And then since we're using just additive, XOR secret sharing really, this is still a valid secret sharing of these entries. It's just, and then server 2 does the same thing. And, oops, great. And so now we have essentially added the dummy reports to the bottom of our record. So I guess one sort of asterisk to note is this does reveal the total number of dummies that you're adding across all records. We actually got a bunch of viewer comments about this. But this is okay, because if you think about it, what we're trying to reveal in the end is noisy counts, so differentially private counts, across all the histogram, but we know that our adversary knows the total number of records that were in the directory, in the data set to begin with, right? Because they collected all the records. So basically, they could already compute the number of dummies that were added just by adding all the totals in the histogram and then subtracting off the initial number of records. So it's not actually teaching them anything new. It does mean we need like a slight variant of differential privacy, which exists out there. We found it in Sullivan's textbook. So but it's a slightly, I guess, less general because it assumes you already know the number of entries in your data set. But for our case set, that's true. Yes.
With the sensitivity to sensitivity is not 1 anymore because we revealed the.
Yeah, yes. Yeah, that's true. Yeah. So it's going to change the sensitivity in the function, but we can take that into account. So it just changes our differential privacy bounds very slightly. But yes.
I
Yes.
may wind up asking this on each slide,
Yes.
but where is the MPC required on this slide? It
So-
seems like,
We've just gotten rid of the MPC.
Okay, good.
So initially they said you use MPC to generate a bunch of Gaussian numbers, secret shares of Gaussian numbers, use MPC to generate dummy records, like that number of dummy records, and a bunch of like dummy records at the bottom so you can pad up to a total so you don't even reveal this
so
count.
the individual ones don't bother with MPC, they just.
Yeah, so
create
now
whatever.
we've gotten rid of the MPC and we replaced it with just each party doing a bunch of sampling and generating some records. So much more efficient. And the goal is sort of get rid of the MPC everywhere
Yeah,
because
yeah.
it's a general MPC is not going to make for a practical protocol, particularly because we want these to be really big sets. So the experiments we did were up to like 10 million, I think. So that's not going to work with MPC. Okay. Any other questions? Thank you for all the questions. All right. So I'll just note, because we're talking about differential privacy, that analyzing the total privacy budget is a super complicated thing because of the way that differential privacy sort of aggregates over many queries. You can do a trivial aggregation where you just add things up, but that gives you a much higher total privacy loss than is actually the case. So, so we use a privacy accountant, actually, from Gopi et al., so from folks here at MSR, which made our results much better and the process much easier. Okay, so that's all I'm going to say about the first step. So now the second step, which is looking at shuffling. So again, the idea is that we have these, each party has a share of each record in the data set. We want to re-randomize the shares and shuffle them so that now you can't tell what went where, but we can still have shares of the same entry, the same records. So if we want to do two-party shuffle, there's sort of two different approaches. So one is using public key encryption. So basically, it would say, maybe one party could encrypt each of the records with a randomizable public key encryption scheme, and then the other party can sort of shuffle them and re-randomize the encryptions and then send them back, and then the first party can decrypt them. And now they have them in different orders. Now, if you want to re-randomize shares at the same time, you actually also need like a homomorphic scheme so that the party, in addition to sort of re-randomizing the encryption, they can also sort of re-randomize the secret sharing, so they can like add a little delta and store that and add that to their own share and then re-randomize it. So making that work is a little bit tricky, particularly if we want, here we were able to do everything with like binary secret shares, and that's not going to work well with public key encryption in general. It might be interesting to look at doing this based on like some kind of lattice-based scheme that's sort of inherently already does sort of bitwise encryptions, but we didn't want to go that way. We wanted to stay away from public key encryption.
I know
Yes.
it's beyond your model, but
Yeah.
if you do it homomorphically, you can also prove that you did the shuffle correctly. That's all
Yes,
just
yes.
Depending on.
Yeah, no, I think that's interesting, and that is something. That's one of the things we talk about in the open problems is that like proving stuff would be good, but there's no reason that we couldn't prove things with this approach as well. I guess, although we don't, so at the moment. Yeah. So then the other approach that's out there for doing two-party shuffles is using a sorting network. So basically, you have a big circuit, which is essentially or I guess a big network. All of your records start out over here, and then they each go through a bunch of sorting gates, which either swap them or don't. And you can sort of basically generate a random permutation and get from that random values of the sorting gates, and you sort of compute each of these like swap or not things obliviously so that the parties don't know what got swapped or what didn't. But sorting networks take n log n gates, so now you blow up the cost by an extra factor of log n, which if you're dealing with like 10 million records is actually non-trivial. So we don't want to do that either if we can help it. So what we do instead is we sort of cheat and we add a third party, which makes things easier. Theory being sort of if we can find two parties that we're willing to believe are non-colluding, probably finding three parties is not that much harder. And so I'm not really going to talk about how this works, but just to give some rough intuition, the idea is that, say for servers 1 and 2, they're going to share a permutation, and they're going to share like a secret permutation that they know that server 3 doesn't, and a mask that they know that the server 3 doesn't. And so each of them will permute their shares by the permutation and mask it by the mask. And then say one of them will send it to server 3, and again, server 3 is going to share a permutation with the other, each of the other two, and they'll permute the share that they have with the shared permutations. So you end up getting something that's been permuted by, according to all like pairs of shared permutations, and masked by all shared masks, and where you've done the same operation to each of the two shares. So the really nice thing, I think, is that all we have to do is locally permute, and so permute with a permutation that you know, and apply a mask, which is an XOR. So the operations are super simple. So even though we have a lot of records, it's really easy to do. And then we have to send, blah, blah. Basically we end up sending essentially the size of the secret shared data set. So each one set of shares, I think one set of shares, I don't remember, from S1 to S3, and one set of shares from S3 to S2, or something like that. So it's a relatively small computation. It's like twice the size of your initial unencrypted records, which for communication is pretty low for this kind of protocol. And just note that you can see this as sort of like, there's a paper by Mahasal et al. That looks at, in general, how to do like large set operations or database operations on when you have 3 servers in multi-party computation. And this can be looked at as an optimized version of doing two of their permutation protocols. So it's not entirely new. It's sort of optimized from what they have. But yeah, this ends up being like way later weight than anything you could do with public key encryption, because we don't need any public key encryption at all. Like everything is just secret shares. Okay, and then, so this step is sort of trivial. We don't have to say how to do that efficiently. You're just opening the shares, so reeling the shares to one another. And then again, the sorting, the partitioning is trivial. And then the last step is, I said, if we wanted to, we could look at a particular bucket and add up the values for the numerical attribute. And so the question is, how do we do that? Well, so roughly homomorphic encryption is what we want to use. So if we encode the numerical attributes as additive shares in ZP, then, and dummies can use shares of 0, so they don't even count. So we get, don't even have to consider them in the noise, which is sort of cool. We can, when we do these shuffles, we can sort of re-randomize the categorical shares, according to a bitwise sharing, and then re-randomize the numerical shares according to this additive sharing in ZQ, and that all works nicely, which is cool. So I guess the question is just like, and then the idea is at the end we just, each of the parties adds up all the shares that they have, and then the sum of those, and maybe add some small noise, and then the sum of those two shares gives you the actual answer, mod P. The question is, what is P? So we want that, when you add everything up, you don't overflow. Like to add up the values in the clear, you don't want them to overflow. Because then you sort of corrupt your results, because you're going to take everything mod P. But then that works great if all the clients were honest. Everything is super easy. You just figure out what the maximum value of the attribute should be, and you take that times the number of clients, and that's the next largest prime is what we can use for P. But but we don't assume all the clients are honest, so we need to deal with users that might encode values are in the wrong range. So there's a couple of approaches out there to do this. So this is one of the things that Precio looks at a lot, because as I said, they basically add up vectors of numbers. So one is basically a very optimized sort of zero knowledge range proof to try to prove that it's actually in the right range. I forget, they have a cool name for it, which I don't remember at the moment. And then a SNP, yes. And then there's Precio Plus, which instead does a Boolean to arithmetic secret share conversion. So the clients sort of encrypt things or encode things initially bitwise. So it's really easy to see what the length of any client input is because you just look at how many bits there are. And then the servers do a protocol to convert that into something mod some larger p, much larger p, so that you have room for overflow. So that prevents users from submitting something too big, but it's a bit expensive. So what we actually use is this cool protocol called quotient transfer, which was in these two papers. And so they are basically, it's somewhat like the Boolean approach. So the client share an input in ZP, which is going to be relatively small, so just a tiny bit larger than whatever the maximum, or just big enough to include whatever the maximum attribute that you want. And then the servers will run a protocol that converts that into the larger P that we actually want. And so since you had to encode the thing, as an input, mod this, secret shares mod this a smaller P, then that sort of gives you a maximum. Even the adversarial, a malicious client can only encode something that's P minus 1. That's the biggest you can get. And then we do the share conversion to bring it into a larger field so that we can do the addition with that overflow. And the cool thing is it's super cheap, so it costs 1 bit OT per conversion. And it turns out when you have 3 servers doing bit OT is like trivial. It's again, I think, like 1 bit per OT. So here we're doing like I think something like 1 bit of communication per record. Is that accurate? A few bits in any case, a few bits of communication per record, something like that. So it ends up being very efficient. Yes?
So does the P prime have to be very much larger than the P? I mean, like you mentioned trivially, you just have to multiply it by the number of clients again, right? So
Yeah, I think that's what it is. Plus a little extra, but yeah. Does that?
Yeah, that's
That's Will is our resident extrovert on the quotient transfer. Cool. Okay, and so just to see like how this fits into our protocol, we can actually do the first steps using these small shares, which is also nice from a communication cost efficiency. I mean, basically all cost efficiency. And then just before we want to do the aggregation, so once we've already got things partitioned and we're looking at a particular bucket and we just want to add up the numerical fields for that bucket, we'll do this quotient transfer to expand things to the bigger size. Boop, boop, boop. Okay, cool. So that took care of the first thing. I'll go through these a little faster maybe, but okay. So I guess the next question is what happens when we want to handle really large attributes? So I said that in order to get the differential privacy guarantees we want, you have to look at the attribute and basically say, what are all the possible values that the bits in that attribute could take or that attribute could take? And I'm going to sample a dummy record for each one. So, sorry, sample a number of dummy records from a Gaussian for each one. So that's potentially a lot of records. And if you actually, and the number of dummies, you notice, doesn't actually even depend on the number of records you have total. It depends on just like how many possible attributes you are here. So you're potentially adding a whole lot of dummies, and it grows exponentially with the bit length of your attribute. So at some point the attribute is going to be too long, and we just can't do this practically anymore. But we now know we can do this sort of recursive partitioning. So the idea is we'll just split this big attribute into 2 attributes. So now say we have our 6-bit attribute. We'll first partition on the first 3 bits, and we get a nice histogram like this. And then we say, OK, well, some of those buckets are really small. They're swamped by noise anyway. We're not going to get any useful information out of them. We'll ignore them. And then we'll partition on the remaining only on the remaining 3 buckets. So this means we end up having to add less noise. And particularly for data sets that are sort of skewed, that have a bunch of like really heavy nodes and then a sort of long tail, this works nicely. Yeah, so it gives you a bit of like a heavy hitter sort of thing. Not exactly, but something like that. Yeah, so this means that we can now like deal with very sparse attributes, very long, very sparse attributes. And we do one of the experiments which has, I think, 256-bit attributes, and we just keep splitting it over and over. I think we do 16 bits at a time, 16 times.
With the ZF distribution for the data that we have, which is the table that you mentioned, that we can nicely prune.
Yes, we do this experiment with the distribution that works nicely. Yeah. Yes.
What's the threshold after which you prune? Like, So
So that's something you sort of have to tailor. And you can actually, even the analyst can, I think, look at it at this point and see what the distribution is and could decide where to put that level. It affects your accuracy and then your efficiency, because.
do you know what distribution you'll get in the end? Like, will it be the same? No.
Yeah, so I don't. It's not like a nice heavy hitter because you're doing this over and over. So no, but we can say that the results are differentially private. Basically, we think of each of these levels as sort of a differentially private query. So in that sense, we can give you differential privacy bounds, but I can't. The accuracy bounds are a little hard. We do have some bounds, but it's not easy to summarize it in a nice distribution.
Do you always do just like the first 16 bits and the next 16 bits and the next, or do you try to be clever about like choosing more or less selective bits?
I think we are not doing anything clever on the number of bits. We're just for these experiments. You could think about doing something more clever, but at the moment we're not. Yeah. Okay. All right. So there's that, and then maybe one more thing. Which is basically how, I'll go through this relatively quickly, but so how do we recurse without the noise blowing up? Because if you see, we add some number of dummies, and then those dummies don't go away the next record, right? Like, so now there's still, all the dummies in Australia are now sort of split up across these, and we've added another layer of dummies. And then if we go and do another partitioning, we're gonna add another layer of dummies. And so you would think that, and we can add quite a lot of dummies relative to the amount of data. So it's sort of, it ends up being that a lot of the cost is just shuffling around these dummies. So we'd like to be able to at least clean up the previous level's dummies before in the next level, and we can. The idea is that when we add these dummy values, we'll set the particular attribute to whatever it is, whatever dummy bucket we expect it to be. So the country attribute for those dummy values would originally have been Australia. But then for all the other attributes, we'll set them to something special. Think of it as like a dummy attribute that says whatever bits encode dummy. That's sort of outside of the space used by real attributes. And so now when we do the next level partitioning, say based on browser, we can just add another bucket there that's the browser equals dummy. And so all the dummies in the previous record end up there with noise. And you can actually show that this is basically, in terms of differential privacy, equivalent to doing like one more differentially private query on the attribute partition, on the attribute counts. Maybe I'll sort of skip sort of faster with that. So it's sort of nice because you sort of magically clean them all up. So because we're rushing, I'm not going to say much about the implementation, but there is an awesome implementation in Rust that Kim made. And it's up on GitHub, publicly available. It has client and server components, and it allows you to flexibly adjust the types of attributes and the attribute lengths and things like that. It supports this kind of arbitrary histogram exploration and the sums. So it does everything, and everybody should try it out and play with it. That's one of the things we're hoping for putting it out there, is that we get people to try it out, because we think it should compare favorably with the competing approaches. I just mentioned about performance. So we did some experiments with 10 million records, as I mentioned, and at privacy budget of 2, which like total over the query, and which is in line with what most of the industry standard seems to be. So you can see for different record lengths, we're getting times in seconds and communication in megabytes, which is not too bad. From when we get up to 32 records, we actually did it in 2 layers and did some pruning and hiding information about what the distributions were. But again, the time is still reasonable for 32 bits. And then we did a somewhat smaller data set, so 400,000 records, still pretty big, where we had 256-bit records, and we did this many-layer thing. And that, again, took like times in the hundreds of seconds, so still feasible. Yeah. And I'm just really, really briefly going to mention that there are, I think, a bunch of open problems. I think one of the cool things about this is it's a different approach than what other folks are looking at. So that means that there's a lot of open space for work, for future work, and for improvement. So I guess one thing is sort of what you alluded to, Josh, is that you could think about getting correctness even when the servers are dishonest, which is sort of nice. If the reporting origin is a third party, it'd be nice for them to be able to say, like, actually, I'm getting the right answers, right? So that would require a bunch of just sort of different extra work in terms of even just like making sure you're getting the right inputs, in terms of probably making sure you're not adding too much noise to any one attribute, so making sure that the noise sums are in a bound, and then getting sort of malicious secure shuffle. And there are sort of techniques to do each of them, but finding the sort of the optimal way to do it, I think, in a way that doesn't blow up the cost prohibitively, is definitely going to take some work. Would be and may require some interesting techniques. I guess the next thing, which I'm personally even more interested in, is privacy versus when one of the servers is malicious. We're still going to need them to be non-colluding, obviously, but we could hope for privacy when when one of them behaves arbitrarily badly. And that's a little tricky. We actually don't really have a text, but we also don't know how to prove anything about it. So I think one way or the other would be interesting. And in particular, one thing that's hard to analyze, if you think about what happens if the servers flip some bits in their shares. So if they fit bits in the shares up here, okay, it's just like you're modifying that record. So that shouldn't, maybe doesn't make that much difference. But you could also flip bits in the dummy records, like so the other guy's dummy records, and it's really not clear how to analyze what effect that has on the resulting total. So now somehow you don't know what dummy record you're affecting, but somehow you've taken some dummy record and moved it from one bucket to another, and that at least throws my analysis skills in terms of differential privacy, out the window. So it would be really interesting to have somebody who knows the area better look at that question. Another thing that I think would be really cool is to look at better differentially private budgeting, like when you do multiple queries. So some of the things that they've done in the more relevant to like the secure hardware space is you can actually track differential privacy budget, like the privacy budget separately for each record. So you can say like how many queries was this record actually involved in. So if the user lives in Australia and most of the queries that are happening are in the US, then sort of that user hasn't, their records haven't appeared in many aggregates, so their budget is still very small. And so then you can do more queries on Australia later, and that's okay, things like that. And you can get very, very subtly if you can like track individually what the privacy budget remaining is for every individual record. One tricky thing is that the privacy budget itself is then a private attribute because we know it depends on which queries were relevant, were satisfied by this record. So you end up doing sort of like a noisy estimate of the privacy budget for every record, like a very noisy one, and then you use that. So anyways, there's some interesting techniques there, and figuring out how to apply it to this sort of like MPC shuffled secret shared approach, I think is really interesting. But we didn't have time to do it. Yeah, so Cookie Monster is the one that applies it in the like more like secure hardware sort of setting. And I guess the last thing is when we're getting a bit to like saying exactly what kind of distribution we get when we do this layered thing. I think at the moment it's not exactly heavy hitters, but maybe we could get something more like a formal heavy hitters guarantee using some of the techniques that's out there, because there's been a lot of work on that. Yeah, so that's about it. This appeared in CCS last fall, and the paper's up on ePrint, and the code is on GitHub. Thanks.
Any more questions?
This may be, feel free to give this debate a tool, but I'm curious about the quotient transfer. Does that work when the original P is 2?
No, it was not.
Okay.
It's actually a very underappreciated idea. I really liked it, and yeah, I hope people can take interest on that. It was good.
You should give everybody 4 talks.
Oh yeah, actually, it's a good idea.
I know I sound like a one-trick pony, but there's a lot of overlap between this and some of the voting techniques. We can't do differential privacy again, of course, yeah. We can't.
No easy
Not a good
voting
idea
results,
to
that's good.
Randomize the votes a little bit. You know, like, we have the same problem of, you know, we are taking a bunch of small values and adding them up, and we have to make sure the total doesn't overflow. So that's why the quotient transfer. And we're doing the same kind of, no, well, not what you're doing, but the approach of zero knowledge proofs that they're all zeros and ones or all within the range.
We can check that actually, but I'll talk to you.
Yeah, please.
I don't know if it works with malicious security. Does it give malicious security?
There is a version of it, but I didn't check the changes and the proof much. It was enough for us, but there were mistakes. It was enough for us.
Yeah.
And I said,